Okay, welcome back. We're learning techniques of integration. This is the first technique that really doesn't kind of rely on a U-sub or anything clever from algebra. Where does this kind of technique come from? You can derive it from the product rule. So recall how the product rule worked. And in that case, you had the derivative, we'll say with respect to x, of these two functions. We'll just assume they're functions of x. So if you take the derivative of this, you'll get u times the derivative of v with respect to x plus, leave v alone, times the derivative of u with respect to x. Okay. I'm going to integrate everything with respect to x, and you can do that. That's no big deal. Okay. And integrate both sides of an equation. On the left here, from the fundamental theorem of calculus, this derivative and that integral will cancel each other out. You just get u times v. On the right, we can rewrite stuff with kind of the chain rule, sort of. There's a dx's cancel, so you just get u dv, and then plus the integral of v du. These dx's cancel. Then we're going to solve for the integral of u dv. Okay, so the integral of u dv is equal to u times v minus the integral of v du. Okay. To apply this, basically you're applying it to an integral where you have a product of two functions, or you not necessarily are able to do a u-sub of any sort. You have to determine which part is u and which part is dv. Okay, and so let's dive in here to example 1 and kind of just go at it. All right, so this is section 2, pretty much how it works. We want to do example 1, and we're looking at the integral of x e to the x dx. Okay. Okay, so I want to figure out what is my u and what is my dv. And usually they do a little table. So u, I'll let be x, and my dv, the part of it, the integral that's dv will be the e to the x dx. Okay, so with the u part, I'm going to take the derivative of it. So the derivative of u du is just dx, the differential form of the derivative. Okay, so the derivative of 1 is, the derivative of x is just 1, and then tack on the dx. Okay. For dv, to get the v, I'm going to have to integrate. So the integral of e to the x dx is just e to the x. Right? Okay. Then on the other side, I can use that information to sort of fill in the blanks in that blue box there, right? So I go u times v, which is this times this, and in our case that will be x e to the x, and then minus the integral of v du, which is this times this. Okay. So I'll have e to the x dx, and then that second integral is simple. Elementary, so you can integrate that to just e to the x and then plus c, and you're done. Okay, okay, so fairly simple idea. How did I know which one to pick for x and which one to pick for u and which one to pick for dv? They give you an acronym in the book called LIATE. So L-I-A-T-E. L for logs, I for inverse trig, A for algebraic, so anything that's like a polynomial or a square root, T for trig, and E for exponential. So if you look at our function above in example 1, we have x and then e to the x. The x is considered algebraic. It's like a polynomial, just one-term polynomial. And then the e to the x is exponential. The algebraic comes before exponential, and this determines whichever one comes first is going to be your u. Okay, the function that comes first is u. Honestly, you're going to be forced to do do one or the other. If you pick wrong, that second integral will usually snowball. In other words, it'll get worse and worse and worse. Or when you're doing your little table here, you just won't be able to do the integral of dv. So you'll be forced to use the other one. So it's basically forcing, but if you want to use the acronym LEAT, by all means do that. That makes my life easier too. Okay. So let's take a look at another example. Here we go, example 2. And we have the integral of x squared ln x dx. Okay. So from LEAT, we'll say ln x, right? The log comes before the algebraic. So dv then is the x squared dx. The derivative of u is 1 over x dx. And then the integral of x squared for v will give me x cubed over 3. And I'll box all this junk off. So the integral will equal u times v, so x cubed ln x over 3, minus the integral of v du. So that will be, I can factor out 1/3. X cubed over x will just be x squared dx. And again, that's an easy integral, just a power rule. It's x cubed over 3 plus c. And then we can clean it up a little bit and we'll have our answer. Okay, great. Okay, so sometimes you're only going to have like one function in your integral, and you're like thinking, Leah, okay, so what do I do? You just pretend one of the functions is the number 1. Okay, so for instance, example 3, integrating arc sine of x from 0 to 1 dx. Okay, I can't integrate arc sine, so you're definitely not going to make that your dv. You'll make it your u. Right, so I have arc sine of x for u. dv, then just make 1, right? 1 dx. Okay, so v integrating 1 dx is just going to give me x. The derivative of u is 1 all over the square root of 1 minus x squared. And I can box this junk off. Try to keep your work nice and neat so other people can read it. U times v is x arc sine x minus v du is the integral of x all over the square root of 1 minus x squared dx. And then you could do a u sub on that second integral for the stuff inside the radical. Du will be negative 2x dx. And then dx will be negative du over 2x. So you got a 1/2, negative 1/2 constant floating about eventually. Let's see, we have x arc sine of x minus the integral of x all over now the square root of u times dx, which is negative du over 2x. So I'll have x arc sine x minus what will become plus 1/2 integral. The x's are gone. 1 over u, square root of u is really u to the negative 1/2, so let's just write it that way. Then I have x arc sine x plus 1/2 u to negative 1/2 plus 1 is 1/2 times the reciprocal will be 2 over 1. I have to remind myself to integrate or to evaluate. This is a definite integral, so I have to put the little bracket on to remind myself. This will be x arc sine x plus u to the 1/2. U is 1 minus x squared, then to the 1/2, and we evaluate from 0 to 1. Plugging 1 into the antiderivative. Arc sine of 1 is pi over 2, so that would be 1 times pi over 2. Plus 1 minus 1 is 0, so that would just be 0. Minus, plug in 0, you get 0, plus 1 to the 1/2. So that would just be pi over 2 minus 1. All said and done. Great. You can do you could do integration by parts more than once. Okay, so I guess maybe let's do a different section. Okay, so section 3. Repeated by parts. So our example number 4, I'm doing the integral of x squared sine x dx. And I'm going to start with an integration by parts. So I'm going to let my u from Lie, the algebraic first, so x squared, and then my dv is sine x dx. So my v, the integral of sine, is negative cosine x. Du would be 2x dx. Okay, so my box, that chunk off. So this will be negative x squared cosine x. And this is where it's going to get a little bit annoying doing these multiple by parts. Then minus the integral of v to u. But it'd be, there's already a negative kind of in there, so it's going to be plus, you can factor out 2 integral x cosine x dx. Okay. That thing I can't integrate either, so I think maybe I could do by parts on it again. So I'm going to do by parts just on this guy. So again, the algebraic comes before the trig. So I have u as x and dv is cosine x. If you let x be your dv, it would integrate up, right? It would become x squared, and your integrals would start snowballing, so they get worse and worse. So again, it's a forcing thing. It's not like you really have to memorize Lie, but here we are. Anyways, dx, right? And then v is the integral of cosine. It's just going to be sine x. Du is just dx. And then we should have something we can integrate, right? So this is going to be negative x squared cosine x plus 2 times u times v, which is x sine x, minus the integral of v du, which is just the integral of sine x dx, which we can do. Okay, so we're getting negative x squared cosine x plus 2x sine x. The integral of sine x is negative cosine x. There's a negative in front, so negative will become plus, and then 2 cosine x plus our integration constant c. Let's just make sure we're right. Negative x squared cosine, then 2x, and then 2 cosine. Yeah, we're good. Okay, so you can do it over and over. There's nothing illegal about that maneuver. You can do that. If you get a really nasty one, you could do something called the tabular method, okay, which is kind of clever. So for instance, we could do the same integral doing the tabular method. I don't advise doing the tabular method because you always kind of forget it after a while. But anyways, the way it goes is you kind of do a column of alternating signs. Okay, you start with plus, minus, plus, minus. Then you do a column of u and its derivatives. So derivative. And then you do a column of integrals. Okay. So the one you're going to be doing the derivatives of is the one that's going to go away, the x squared part. Okay, that's u anyways from Lie. So you would have the x squared, and then you go 2x, and you keep on going until you get 0, and then 2, and then you're done. Okay, so for the integral, you'll have sine x, and then cosine, negative cosine x, negative sine x, and then finally cosine x. And then the integral, so if you have the integral of x squared sine x dx, it's just going to be this times this times this. So we would get negative x squared cosine x. And then it's going to be this times this times this. So negative is positive, 2x sine x. And then this times this times this. So plus 2 cosine x plus c, right? But like I said, it's not necessary to really ever memorize this. You could do it in general, and I did a video last year where I use the tabular method all the time. You could do it. It's kind of hard at least for me to remember because I learned the by parts kind of the hard way first, and then somebody said, hey, by the way, So anyways, there's the tabular method. It's there if you want to use it. You don't have to. If you do, you can use it. I don't care. Anyways, let's go back and kind of look at this one crazy one, example 5, or maybe even before example 5. Let's do a different one. And I call these loopers. Okay, so section 4, a looper. It's because you end up back where you started. So this is just an example. We can try one of the, if I can find a looper in here. Okay, so number 9's a looper. We could try that. That'll be fairly simple. I want to make it a little harder though. So in my example, I'm going to do the integral of e to the x sine of 4x, just to make life worse. Okay, so let's take a look at this guy. These are pretty weird, and I think you'll find it kind of interesting. But anyways, I'm going to do my u sub as usual. Lee says trig before exponential, so I have sine 4x for my u, and then dv is going to be e to the x dx. So v will just be e to the x, and then du will be the derivative of that, right? It's cosine 4x, and then chain rule times 4. Okay, so this should equal, and if you allow me to, let me move this over. It'll be easier for you to kind of visualize what's going on if I move this over here. Kind of keep it away from Okay, so this is going to be u times v, so e to the x sine 4x minus the integral of v du, so that would be 4 integral of e to the x cosine of 4x. And if you look at what's going on, it doesn't seem it's changed much. And somebody decided, hey, let's go ahead and do by parts again, and we'll do by parts on this guy. Okay. So again, from Lee trig before exponential, so I have cosine 4x, and then dv is e to the x dx. So v is e to the x. And then du is going to be negative 4 sine 4x. Okay, okay, so then, what do I have? E to the x sine 4x minus 4 times uv, so e to the x cosine of 4x minus v du. Integral of v du, that will become plus, you can factor out 4, and you have the integral of e to the x sine 4x dx. If you look at what we're getting now, 4x minus 4 e to the x cosine 4x minus 16 integral e to the x sine 4x dx, we're back to where we started, right? Let me carry down the other side. And look at this equation, right? Look at it now as an equation as opposed to just simplifying an integral. What do we want to know? Well, we want to know what this integral equals. Okay? That integral is right there. It's also over here. So what do? Well, you can replace it with a variable, and usually the books just use I for that thing I circled in red. And then you have I equals e to the x sine 4x minus 4 e to the x cosine of 4x minus 16i. And then to get the answer for the integral, you just solve for I. So add 16i to the other side, you end up with 17 i's. There's got to be an integration constant somewhere we could tack on. Let's see. And then just divide everything by 17 and you have your answer. Okay. So I call them loopers. And that happens when both derivatives are kind of cyclical. So when you take its derivative over and over, you end up right back where you started. Okay. And so it only happens when both your functions are of that type. So if you kept taking the derivative of e to the x, eventually you'll get back to e to the x. Only take one step. It's actually always e to the x, right? If you keep taking the derivative of sine, you're eventually going to get back to sine. So when that happens, you end up with a looper, and you have to do this substitution, which I think is pretty cool. Right? Okay. Let's look at that one in the book, which is kind of a nightmare. The secant cubed problem. Let's see if I can remember how to do it. Okay. So this will be the last problem. We'll make this the video quiz. And what example is it? 5. Okay. Example 5. So this is the video quiz, video quiz, video quiz. And this would be the second video quiz and video quiz set number 4. Let me just mark it in my notes what we're doing. Example 5. Okay. Right. So we wanted the integral of secant cubed. This is not an integral we can do off the top of our heads, but we can use integration by parts in sort of a clever way. So the cleverness of it is you're going to let u equal secant x, and then dv equals secant squared x. Because you can integrate secant squared, right? Secant squared, the integral of that for v, of course, is secant squared x dx. V will be, the integral of secant squared is just tan x, and then the derivative of secant is going to be secant x tan x dx. Okay, so we need that material. Let's move that to the side so it's not contaminating all of our work. Yes, I'm going to push it over here. Thank you. All right, so I'll end up with the integral of u times v, or sorry, just u times v, so secant x tan x minus then the integral of secant x tan squared x dx. Okay? So we'll do a whole chapter here on trigonometric integrals, but the long and the short of it is that you're going to want to convert the tan squared using those Pythagorean identities. Remember, sine squared plus cosine squared is 1. If you divide by cosine, you get tan squared plus 1 equals secant squared. So tan squared is actually equal to secant squared minus 1. Okay, so tan squared is secant squared x minus 1 dx. Then what you're going to do is distribute that secant. So you get secant x tan x minus the integral of secant cubed x, and then minus secant x, and all this in parentheses, dx. And what you notice probably is that this is a looper. Okay, so we write it secant x tan x minus the integral of secant cubed x dx plus the integral of secant x dx. And so there's basically a secant cubed on both sides, right? So we replace the secant cubed with some variable. I'll say I. Then I have secant x tan x minus I plus the integral of secant. You probably, that's not one of the ones I force you to memorize, but it's the ln of secant x plus tan x. And then, of course, we have that integration constant. Move the I to the other side, so add I on both sides. You get 2I equals secant x tan x plus ln absolute value of secant x plus tan x plus c. And then finally, just divide by 2 and you're home free. Okay. So that's our video quiz for the day. I'll also finish up this video for me, as usual. Thank you for watching, and hope I see you next time. Okay. Thanks for watching.